We know the electrons are generated at electrolyte. We are going to discuss about the electrolyte, break down the chemicals into its parts. Na plus ions move towards the electrode, take that one Na plus ion consumes one electron to become sodium, charge on one more. When we add water, the rubidium reaches the cathode, the size is increasing. Strong electrolytes obey Debye-Huckel-Onsager's equation. Second one is nature of solvent and its viscosity. When it increases, ionic mobility or movement decreases. Hello students, welcome to Learn It. The electrons are generated at negative terminal of the battery and consumed at positive terminal. So with respect to electrochemical cells, we have already discussed about the galvanic cell. So let us begin with the electrolytic cell. It's a device in which electrical energy from external source is used to perform chemical change. So as the name suggests, electrolytic, it means we use the electricity and break down some chemical. So let us look at an arrangement of electrolytic cell. Consisting of three parts. First one is battery. We know battery acts as a pump of an electron. Second one is electrode. Third one is electrolyte. So with respect to electrode, we are going to discuss about three main aspects. First one is deposition and liberation. Second one is Faraday's laws of electrolysis. Third one is products of electrolysis. Here we use some chemicals and we are going to analyze what products we are going to get at electrodes. Next comes with respect to electrolyte. We are going to discuss about the electrolytes and non-electrolytes. And the last part is conductance. The type of compounds used in electrolytic cell are ionic compounds. So let us look at how electrolytic cell works. So when battery starts to provide the electron and consumes the electron, the cations starts to move and consume those electrons provided by negative terminal of the battery. Anions move towards the positive terminal of the battery. The separation of anions and cations in an electrolytic cell. So this is how we are going to break down the chemicals into its parts. So let us look at the electrodes. We have taken molten NaCl. So it consisting of Na plus ions and Cl minus ions. So the environment consisting of electrolyte, which is containing Na plus, Cl minus, Na plus, Cl minus, which is in contact with the electrode, which is connected to negative terminal of the battery. So as we can see, negative terminal of the battery is providing electrons. So here the Na plus ions move towards the electrode, take that electron. So here gaining of electron takes place by Na plus ions, so it is called as reduction. So the place where reduction takes place is called as cathode. So in conclusion, we can say that whatever the electrode which is connected to negative terminal of the battery is called as cathode. So like this, many Na plus ions get deposited on the cathode. So this is called as electrode deposition or it is happening at the cathode, it is called as cathode deposition. So it further pushes Cl minus ions away and attracts Na plus ions. Let us look at the other electrode which is connected to positive terminal of the battery. So here we can see the electrons are consumed by the electrode. That's why this electrode is positively charged. So as it is positively charged, Cl minus ions get attracted, and this Cl minus ion or chloride ion loses one electron. So this loss of electron is called as oxidation. So the place where oxidation takes place is called as anode. So in conclusion, the electrode which is connected to positive terminal of the battery in an electrolytic cell is called as anode. So as the electrons are consumed by the positive terminal, so electrons move towards the positive terminal. Same way, another Cl minus get attracted towards the electrode, oxidation takes place, and it is Cl minus is becoming the chlorine atom. So these two chlorine atoms combine to form chlorine molecule. So this chlorine molecule, it is in a gaseous form, it is liberated at the anode, hence it is called as anode liberation. So it further pushes sodium cations away and attracts Cl minus. In turn, chlorine gas is liberated. At electrode, the terminal which is connected to negative part of the battery is called as cathode. The terminal or the electrode which is connected to positive terminal of the battery is called as anode. So at cathode, deposition takes place. That's why it is called as cathode deposition, but the sign of the electrode is positive, because cations get attracted towards it and the reduction takes place. In the opposite electrode, the sign is negative as anions are getting attracted towards it, and there will be a liberation of gases. That's why it is called as anode liberation. But with respect to galvanic cell, the negative terminal indicates anode because there is an oxidation. Positive terminal is represented by cathode because there is a reduction. So students must understand the difference. So this completes our first part with respect to electrode, that is deposition and liberation. So cathode deposition, anode liberation. So next comes the Faraday's laws of electrolysis. Faraday's laws of electrolysis are also called as quantitative aspects of electrolysis, because here we are measuring the amount of substance deposited or liberated by using the quantity of current we are going to provide. So here quantity of current is measured in terms of electrons or coulombs. So let us look deep into it. So as we know that negative terminal of the battery is connected to cathode, so there will be electrons which are provided by the battery. So consider that battery provided 1 electron. So in the electrolyte, Na plus ions are present. So one Na plus ion consumes 1 electron to become sodium metal and it deposits on the cathode. So like that, if the battery provides another 1 electron, so another sodium atom gets deposited. If it provides another 1 electron, so another sodium atom gets deposited. If battery provides 3 electrons, then 3 sodium atoms get deposited. So sodium metal deposition takes place. If battery provides 100 electrons, then 100 sodium ions get converted into 100 sodium atoms and deposit on the electrode. If the battery provides Avogadro's number of electrons, that is 6.022 into 10 to the power 23 electrons, then Avogadro's number of sodium ions get converted into Avogadro's number of sodium atoms. Let us look 6.022 into 10 to the power 23 in terms of coulombs. So charge on one electron is 1.6 into 10 to the power minus 19 coulombs. So charge on two electrons is 1.6 into 10 to the power minus 19 coulombs into 2. If it is 3, then 1.6 into 10 to the power minus 19 coulombs into 3. So like that, if we take 100 electrons, then charge on 100 electrons is 1.6 into 10 to the power minus 19 into 100. If you take 1000 electrons, then charge on 1000 electrons is 1000 into 1.6 into 10 to the power minus 19. So that 1000 is indicated by 10 to the power 3. If we take 10 to the power 10 electrons, then charge on 10 to the power 10 electrons is 1.6 into 10 to the power minus 19 coulombs into 10 to the power 10. Further, if we take 6.022 into 10 to the power 23 electrons and the charge on 6.022 into 10 to the power 23 electrons is 96,500 coulombs. When we multiply 6.022 into 10 to the power 23, 1.6 into 10 to the power minus 19, we get 96,500 coulombs, which is equal to 1 mole of electron. So charge on 1 mole of electron is 96,500 coulombs. So 6.022 into 10 to the power 23 electrons consisting of charge 96,500 coulombs. So if the battery provides 96,500 coulombs, then Avogadro's number of sodium ions get converted into Avogadro's number of sodium atoms. Now let us further look into how much Avogadro's number of sodium metal weighs. So when we take Avogadro's number of sodium atoms like 1, 2, 3, 4, 5, 6, 7, 8 up to 6.022 into 10 to the power 23, then it shows 23 gram. So 23 gram is weight of 1 mole of sodium. So if we provide 96,500 coulombs of electricity, then we get 23 grams of sodium deposited on the electrode or cathode by the solution. So if we don't provide any electricity, then there will not be any deposition. So this is a non-spontaneous reaction because it is not happening by itself. And the second thing is, we are providing 96,500 coulombs, so we are getting 1 mole of sodium. If we provide double the charge of 96,500 coulomb, then we get the double the amount of sodium. if we get 3 times 96,500 coulombs of charges, then we get 3 moles. It means we are going to get 23 into 3, that is 69 gram of sodium deposited on the electrode. So with this knowledge, we are going to look at the statement of first law of electrolysis. That is, in an electrolytic cell, the amount of substance deposited or liberated at the electrodes is directly proportional to quantity of the electricity passed. So weight of the substance, that is W, is directly proportional to quantity of the electricity passed. Here, quantity of the electricity is passed is measured in terms of charge, like in coulombs. So weight of the substance deposited is directly proportional to amount of charge passed. So W is directly proportional to Q. So Q is the amount of charge in coulombs. So Q is equal to I into T according to electricity chapter. So where I is the electricity in amperes, T is the time in seconds. So W is equal to I into T. So W is equal to Z into I into T, as proportionality sign is replaced by constant. Here Z represents electrochemical equivalence. It is a constant. Mathematical form of first law is W is equal to Z into I into T. So here Z is a electrochemical equivalence, as we already discussed. It means it differs with respect to different materials or different reaction conditions. We are going to look at Faraday's second law. So consider a cathode, one sodium atom deposited by 1 electron, 2 sodium atoms deposited by 2 electrons, 3 sodium atoms deposited by 3 electrons. So total 6 electrons are provided. So 6 sodium atoms get deposited. So 6 electrons made to deposit 6 sodium atoms. So 96,500 coulombs of charge makes 1 mole, that is 6.022 into 10 to the power 23 sodium atoms to deposit on the cathode, which is equal to 1 mole of sodium metal, which is equal to 23 gram of sodium metal. So if we have provided 96,500 coulomb and we got 1 mole of sodium. So if the electrolyte is containing cation which is having the charge +2, for example Cu +2, when we provide 2 electrons, then one Cu +2 ion get attracted and becomes Cu metal or atom and deposit on the electrode. So if we provide another 2 electrons, another one Cu +2 convert into Cu. If we provide another 2 electrons, then another Cu atom get deposited. So here we have provided 6 electrons, but only 3 Cu atoms get deposited. So if we provide 96,500 coulomb of charge, then half of Avogadro's number of Cu atoms get deposited, which is equal to 0.5 mole of copper metal, which is equal to 31.77 gram of copper metal. So here we need to consider that 96,500 coulombs of charge, when we provide, we get 0.5 mole of copper metal. So let us have another case. Electrolytic cell containing Al+3 ion. When we provide 1 or 2 electrons, we are not going to deposit one Al atom because it is +3 and there are only 2 electrons. So we need to provide 3 electrons so as to get one Al+3 to convert Al atom. So if we provide another 3 electrons, then another aluminum atom get deposited. So we have provided 6 electrons and there are only 2 aluminum atoms deposited. If we provide 96,500 coulombs of charge, then there will be deposition of 1/3 of the 6.022 into 10 to the power 23, that is Avogadro's number of aluminum atoms, which is equal to 0.33 mole of aluminum metal, which is equal to 9 gram of aluminum. By this, we can conclude that 96,500 coulombs of charge, if we provide, then only 0.33 mole or 9 gram of aluminum metal get deposited. So by this we can conclude we are providing same amount of electricity, that is 96,500 coulombs, but we are getting different amount of or different mole of substance deposited on the electrode. So in the first case we are getting 1 mole, in the second case we are getting 0.5 mole, in the third case we are getting the 0.33 mole. This is because the amount of substance deposited on the electrode, it is not only determined by the amount of electricity, it is also determined by the valency of the ions, which will convert into atoms. So Faraday provided second law, which is having the statement based on these 3 cases. When the same amount of electricity is passed through different electrolytes, the quantity of the substance deposited is directly proportional to equivalent weights. Here, weight, it is depending on the valency. So equivalent weight is equal to molecular weight, or here it is atomic weight divided by valency. Faraday's second law of electrolysis provides insight of the importance of equivalent weight. So when 1 mole of electrons, that is 96,500 coulomb of charge or electricity is passed, the amount of sodium deposited is 23/1 is equal to 23 gram. Here 23 gram is molecular weight, it is atomic weight and also equivalent weight of sodium. The amount of copper deposited is 63.54 divided by 2 is equal to 31.77 gram. Here 31.77 gram is the equivalent weight of copper because it was in Cu+2 form. The equivalent weight of aluminum is 9 gram. Let us look at the third part of electrode, that is products of electrolysis. So in the study of products of electrolysis, we need to look at 7 compounds. First one is molten sodium chloride, second one is molten lead bromide, third one is aqueous sodium chloride, fourth one is aqueous copper sulfate solution, fifth one is water, sixth one is copper sulfate, but we are using copper electrodes, and seventh is sulfuric acid. So before starting with the products of electrolysis of sodium chloride, we need to discuss something about the electrodes. There are 2 types of electrodes. First one is active electrode. Active electrode means the electrodes which take part in the oxidation or reduction process that is happening within the electrolytic cell. And second type of electrode is inert electrodes. Inert electrodes are the electrodes which do not take part in the reaction which are taking place in the electrolytic cell. The examples for inert electrodes are carbon electrode, second one is platinum electrode. So with this knowledge, let us look at the products of electrolysis of molten sodium chloride. So molten sodium chloride containing Na plus Cl minus ions. So let us take a vessel in which Na plus ions and Cl minus ions are taken, or this is the molten sodium chloride solution as an electrolyte. So it is connected to battery. So negative terminal of the battery is connected to the electrode, so it acts as a cathode. So positive terminal of the battery connected to the any electrode, it acts as a anode. So it is a cathode, so cations get attracted towards it, that is Na plus becomes Na, or reduction takes place. So with respect to Cl minus ions, they undergo oxidation to give Cl atom. Like that another Cl atom forms. So like that these two Cl atoms become chlorine molecule. So chlorine gas liberated at the anode. So products of electrolysis of sodium chloride, molten sodium chloride gives sodium metal that is deposited on the cathode, and chlorine gas is liberated at the anode. So let's go to electrolysis of molten lead bromide. Molten lead bromide contains Pb plus 2 and Br minus 2 ions. So lead ions and bromide ions. So as we know that cations get attracted towards the cathode. So Pb plus 2 ions take 2 electrons. So lead gets deposited at the cathode. So bromide ion is converted into bromine atom. Like that 2 bromine atoms combine to form bromine gas. So electrolysis of molten lead bromide gives lead at the cathode and bromine is liberated at the anode. So next comes the electrolysis of aqueous sodium chloride. It means salt water. So aqueous NaCl contain Na plus, Cl minus, H plus and OH minus ions and water molecules. So here with respect to cathode, there are 2 cations. First one is H plus ion. So H plus ion, it may get reduced into hydrogen atom. So here E naught value is 0 volt. So with respect to sodium, the E naught value is minus 2.71. So this E naught represents the standard reduction potential. We know according to electrochemical series, the substance with the higher reduction potential should undergo reduction. So in between these two, hydrogen is having higher reduction potential. It is minus, it is 0. It means that hydrogen, that is H plus ion, gets reduced into hydrogen. So this reaction proceeds. With respect to anode, there are 2 possibilities. First one is conversion of chloride ions into chlorine gas, whose E naught value, standard reduction potential value, is 1.36 volt. OH minus doesn't get attracted towards the anode in this case, but water gets converted into oxygen and 2 H plus and 2 electrons. Like that, 2 water molecules break down into 4 H plus ions and 1 oxygen molecule is liberated, whose E naught value is 1.23. The difference between the liberation of oxygen reaction and liberation of chlorine reaction is very small. We know here oxidation takes place, so that's why whose oxidation, that is reduction potential value, which is lower, is going to take place according to the electrochemical series. But it depends upon the concentration of the solution. If we take the dilute solution, then water molecules are more, that's why oxygen is liberated. If we take the concentrated solution of NaCl, then even though it has higher reduction potential, the difference between the reduction potentials is less, but chlorine gas is liberated at the anode. So third comes the electrolysis of aqueous copper sulfate solution. So here at the cathode, Cu plus 2 ions convert into copper because the reduction potential value for copper plus 2 ion is 0.34. So therefore copper gets deposited at the cathode. At the anode there are 2 ions. First one is OH minus, second one is SO4 minus 2. Here sulfate ions being bigger, they do not get oxidized at the anode. But as we have seen, water molecules get converted into oxygen of water. So water contains H plus ions, OH minus ions and water molecules. So during the electrolysis of water, we use little amount of acid, that is H2SO4. So that's why we indicated SO4 minus 2 and H plus ions. So at the cathode, H plus ions get reduced into hydrogen atom and hydrogen gas is liberated. At the anode, the OH minus is converted into OH and 1 electron is taken out by the battery. Like that, 4 OH minus convert into 1 oxygen molecule and 2 water molecules and 4 electrons, as they are already got liberated before. Next comes electrolysis of aqueous copper sulfate solution using copper electrode. Here copper electrode is an active electrode which take part in the reaction. So copper sulfate solution containing Cu plus 2 ions, H plus ions, OH minus ions, SO4 minus 2 ions and water molecules. So at cathode, copper plus 2 ions get reduced into copper atom. But at anode, copper starts to oxidize into Cu plus 2 ion and 2 electrons. So the amount of copper deposited on the cathode is equal to the amount of copper which is oxidized at the anode. If we take impure metal at the anode, then we get the pure copper metal at the cathode. So this is the industrial process which is called as electrolytic refining. So here at anode side we use the impure metal which will convert into pure metal by the electrolytic cell. So here we can see left hand side the amount of copper is decreasing. At the right side which is cathode, the amount is starting to deposit. So let's look at anode side. Here copper is undergoing oxidation to become Cu plus 2 ion, and electrons are getting consumed. With respect to cathode, there are electrons, so Cu plus 2 ions are getting oxidized. So within the solution, the Cu plus 2 ions are moving towards the cathode. So that's why the material on the cathode increases. So last one comes electrolysis of sulfuric acid. Here sulfuric acid containing H plus ions, OH minus ions, SO4 minus 2 ions, and water molecules. So at cathode, if we take the dilute acid, H plus ions getting reduced into hydrogen atom. So two hydrogen atoms combine to form hydrogen gas. So hydrogen gas is liberated at cathode. At the anode, like we said before, two water molecules convert into one molecule of oxygen and 4 hydrogen atoms and 4 electrons. If you take concentrated sulfuric acid, at cathode we get the hydrogen gas liberated, but at the anode, 2 sulfate ions getting converted into peroxo disulfuric acid ion. This completes electrode part of electrolytic cell. The electrolytic cell, in that we have already completed about the electrode part in a separate video. Let's look at another part of an electrolytic cell, that is electrolyte. So here it is a liquid component of electrolytic cell. So in that we are going to discuss about two things. First one is electrolytes and non-electrolytes and conductance. First one is electrolytes. What are electrolytes? Electrolytes are the substances which allow the electricity to pass through them, either in their molten states or in the form of an aqueous solutions. It means the substance which allow the electricity to pass through it, and that substance should be in molten state or in the form of a water dissolved solution. So such substance is called as electrolyte. So examples are acids, bases, and some salt solutions. Let us consider an electrolyte. So in electrolyte, ions are present and they are the charge carriers. And when we put the electrodes, which is connected to battery, so even though battery is connected, the bulb is not glowing, because the presence of ions is not only the requirement for the conduction of electricity. So there must be the migration of ions towards the electrode. So the cations move towards the electrode which is connected to negative terminal, anions move towards the electrode which is connected to positive terminal of the battery. So this migration of the ions towards the electrode is called as mobility of ions. So with respect to electrolytes, ionic mobility is the important concept. It consists of presence of ions. Second one is migration of ions. Let's look at the types of electrolytes. Depending upon the number of ions the substance produced, we are going to divide the electrolytes into two parts. First one is weak electrolytes, second one is strong electrolytes. Hence, we are not talking about the substances which are taken in a molten state. So we are only talking about the electrolytes which are in the form of an aqueous solution. Weak electrolytes are the substances which undergo partial dissociation when dissolved in water, whereas strong electrolytes are the substances which undergo complete dissociation when dissolved in water. So in case of weak electrolytes, when we dissolve in water, less number of ions are produced because of incomplete dissociation. Example for weak electrolytes are weak acids, weak bases and weak salts. In case of strong electrolytes, which when we dissolve in water, they are going to have the complete dissociation and more number of ions are produced. Example, strong acids, strong bases and strong salts. So even though if we take exact number of molecules and we put into water, in case of strong electrolytes, all the molecules are going to dissolve into ion. But in case of weak electrolytes, if we take same amount of or same number of molecules as we have taken with respect to strong electrolytes, but very few molecules will convert into ions. So when we pass the electricity through weak electrolytes and strong electrolytes, because of more number of ions, the glow in the bulb is more compared to weak electrolytes, because there are only few number of ions present in the weak electrolytes. That's why the conductance in strong electrolyte is more. Let's look at these examples in detail. So first we are going to look at strong electrolytes. Strong electrolytes contain strong acids. Example, hydrochloric acid, sulfuric acid, nitric acid. Strong bases like sodium hydroxide, potassium hydroxide, calcium hydroxide are also strong electrolytes. Next comes the weak electrolytes. So weak acids like acetic acid, formic acid, carbonic acids are weak electrolytes. Weak bases include ammonium hydroxide, ammonia, aniline are weak electrolytes. So with respect to salts, strong salts, like they are made up of strong acid and strong base. Example here, the salt made up of HCl and NaOH is a strong salt, that is NaCl. Like that, sodium sulfate, potassium chloride, potassium sulfate. These all are salts of strong acid and strong base. So salts of strong acid and weak base are also strong salts. Examples include ammonium chloride, ammonium sulfate, ammonium nitrate. So these all compounds are made up of strong acid and weak base. That's why they are strong salts. So salts of weak acid and strong base are also strong salts. Example, sodium acetate, sodium formate, sodium carbonate. So sodium carbonate, washing soda, it is a strong electrolyte because it is made up of strong base and weak acid. So these all are strong electrolytes when they are dissolved in water. So for weak electrolytes, weak salts include the salts made up of weak acid and weak base. So here we can get ammonium acetate, ammonium formate, ammonium carbonate. So all these are weak salts. So when they are dissolved in water, we get the weak electrolytes. So strong electrolytes undergo complete dissociation. Weak electrolytes undergo partial dissociation, as discussed before. This is all about the electrolytes. Now comes the non-electrolytes. So non-electrolytes are the substances which do not allow the electricity to pass through them either in their molten states or in the form of an aqueous solutions. So generally speaking, non-electrolytes are the substances which are in liquid state. They do not conduct the electricity. Examples include oil, solutions like sugar solution, alcohol, some salt solutions. So in non-electrolytes, there is an absence of ions. So there are no ions, so there are no charge carriers. So when we pass the electricity, as there are no charge carriers, so they do not conduct the electricity. So some salt solutions include solutions of barium sulfate or solution of AgCl, silver chloride. They do not contain the ions, so they do not conduct the electricity and they behave as non-electrolytes. So this completes our electrolytes and non-electrolytes part. So next comes the conductance. So what is the conductance? It is indicated by G. It is the phenomenon or the process of passage of electricity through the material. Its unit is Siemens or mho, which is indicated by the letter S, or the ohm, its inverted symbol, that is mho. So let's look at the types of conductance. First one is metallic or electronic conductance. Second one is electrolytic or ionic conductance. Here the conductance is due to the electrons. In the electrolytic or ionic conductance, the conductance is mainly due to the ions. So here electrons are the charge carriers. So the examples include metals. Some non-metals also possess metallic or electronic conductance. For example, carbon, that is graphite form. We can see conductance through gases by the emission of electrons, as we have seen in J.J. Thomson's experiment, where the gas is taken at the low pressure and high voltage is passed through it. So the gas conducts the electricity. So these rays are moving towards the cathode. That's why they are called as cathode rays. So cathode is positively charged, so electrons are negatively charged. So that's why they get attracted towards the cathode. So this cathode ray tube is used in old televisions. Here no chemical decomposition takes place with respect to the material. So this is the example. With respect to electrolytic or ionic conductance, the charge carriers are ions. Examples include acids, bases, and some salts. They may be in molten state or aqueous solutions. Here the chemical decomposition of the material takes place. Examples include the salt solution. In the electrolytic cell, we are only using the electrolytes. We are going to look at electrolytic conductance further. So we have already seen the definition. So what are the different factors affecting the electrolytic conductance? We are going to look at. Next comes the types of electrolytic conductance. So first one is factors affecting the electrolytic conductance. So there are 5 factors. First one is nature of electrolyte. Second one is nature of solvent and its viscosity. Third one is size of the ions and solvation. Fourth one is concentration of an electrolytic solution. Fifth one is temperature. So students must understand that we are talking about the electrolyte part here. The migration of ions towards the electrode is important. We must understand that number of ions plus freedom of those ions are the key important factors which affect the electrolytic conductance. Let's look into first factor, that is nature of an electrolyte. So in nature of an electrolyte, first one is weak electrolytes, second one is strong electrolytes. We know in case of weak electrolytes there is incomplete dissociation, so less number of ions are produced. In case of strong electrolytes, complete dissociation takes place and more number of ions produced. So we know that number of ions plus freedom determines the electrolytic conductance. So strong electrolytes have more conductance than the weak electrolytes. So even though if we have 100 molecules of weak electrolytes and strong electrolytes, because of strong electrolytes undergo complete dissociation, we get more number of ions, so they conduct more electricity. That's why the bulb in the strong electrolyte glows with more intensity. So second factor is nature of solvent and its viscosity. So we are talking about the solvent in which the substance is dissolved. We are going to look at the polarity of a solvent. So there are two types of solvents. First one is polar, second one is non-polar. Polar means the positive and negative charges are separated, but in non-polar there is no such separation. Example for polar solvents are water, acetone, alcohol. Examples for non-polar solvents are oil, benzene, chloroform. So in polar solvents there are two types. First one is more polar solvents, second one is less polar solvents. Even though the charge separation is there in polar solvents, there is more charge separation, there is less charge separation. Example for polar solvents are water and DMSO. DMSO means dimethyl sulfoxide. This is the structure. Less polar solvent for are acetone and alcohol. So we are going to discuss with the polar solvents because ionic compounds do not dissolve in non-polar solvents. Water, in that oxygen is containing two lone pair of electrons. So the density of electrons is more on the oxygen. That's why we indicate negative on oxygen side, and hydrogen side it is positive because the more density is always on the oxygen. That's why we indicate the other part as positive. So let's take more polar solvent and less polar solvent. If we dissolve our ionic compound, then more polar solvent dissolves the ions efficiently, so more number of ions. But produced. In case of less polar solvents, less number of ions produced, and there are still the compound, it is in the molecular form. That's why the more polar solvent conducts more electricity because of complete charge separation. That's why with respect to solvent, if the polarity increases, number of ions increases, so conductance increases. Let's look at viscosity. So we need to know what is viscosity. Viscosity, it is a resistive force between the layers of the solvent. So if we consider this as a liquid and we imagine that there are many layers within the liquid, and between one layer of liquid and another layer of liquid there is a friction. This friction is called as viscosity. So if this friction is more, then viscosity is more. If friction is less, then viscosity is less. So you can see two examples. In less viscous fluids, the liquid flows more freely than the more viscous fluids. So, solvents can be divided into two parts based on viscosity. First one is viscous and non-viscous. Examples for viscous fluids are honey and gel, etc. Examples for non-viscous fluids are water and acetone. So if we take viscous solvent and if we put the ionic compound, so we know that even though if it is a viscous or non-viscous, if the solvent is polar, then ions are produced. We are taking the same compound and we are dissolving in non-viscous solvent. So number of ions are same, but when we pass the electricity, in viscous fluids or solvents, the ions movement is slower, but in non-viscous fluids or solvents, the ions movement is faster. If the viscosity of the solvents increases, ionic mobility or movement decreases. So conductance decreases. So let's look at the third factor, that is size of the ions and solvation. So let us take ions lithium, sodium, potassium and rubidium. So the size is increasing from left to right. When we add water, we know water is polar solvent, so it has plus and minus charges. So as these ions are positively charged, the negative part is going to surround the ions. So we get hydrated ions. Hydrated lithium ions are having the radius 3.8 picometers, sodium 3.6 picometers, potassium 3.3 picometers and rubidium 3.2 picometers. So that's why size of the ions is increasing, but size of the hydrated ions is decreasing. So when we put these hydrated ions in the electrolytic cell, and as they are cations, they move towards the cathode. Because of the difference in the hydrated size of the ions, the rubidium reaches the cathode faster than potassium, than the sodium, than the lithium. So as the size of the ions increases, the solvation decreases. So ionic mobility increases, conductance increases, except H plus ion. Next comes the concentration of an electrolytic solution. So consider we have strong electrolytes and weak electrolytes. In strong electrolytes, there will be complete dissociation and there is a high electrostatic interaction between the ions. That's why they are having the less freedom. So in case of weak electrolytes, there is an incomplete dissociation. So very less number of ions are present. So when we put water, in case of strong electrolytes, the distance between the ions increases, less electrostatic interaction between the ions or opposite charges. So there is more freedom for the ions to move. With respect to weak electrolytes, as the dilution increases, degree of dissociation increases. It means more number of ions are produced. That's why with respect to concentration of an electrolytic solution, as the dilution increases, concentration decreases. With respect to strong electrolytes, if the dilution increases, freedom of ions increases, so conductance increases. With respect to weak electrolytes, if the dilution increases, degree of dissociation increases, it means number of ions increases. So conductance increases. Last factor which affects the electrolytic conductance is temperature. We know that temperature is a thermodynamic variable. So when temperature increases, kinetic energy of ions increases. So as the kinetic energy of the ions increases, their movement or mobility increases. That's why conductance increases. This completes the factors affecting the electrolytic conductance. So next comes the types of electrolytic conductance. There are three types of electrolytic or ionic conductance based upon the amount of substance present in that solution. First one is specific conductance, second one is molar conductance, third one is equivalent conductance. So let's begin with the specific conductance. So specific conductance is also called as conductivity. So we can understand this concept with an image. So here the conductor is there which is connected to battery. So you know that battery provides the electrons. So electrons within the material also starts to flow. So electricity flows in opposite direction. We already know about it. So before going on to conductance, we need to know about the resistance. Here the electrons are flowing, but the atoms of other electrons also oppose to the flow of these valence electrons. That's why there is the presence of resistance. So resistance is the opposition to the flow of electricity or electrons. So this resistance is directly proportional to length of the conductor. If the length of the conductor is more, then resistance is more. And this resistance is inversely proportional to area. This is the area, surface area of the conductor. So that's why if this surface area is more, it means if the conductor is wide, then this resistance is less. So by combining these two equations, we get R is directly proportional to L by A. So we can replace this proportionality sign with an constant. Then we get R is equal to rho into L by A. Here the rho indicates resistivity or specific resistance. We are not talking about the conductance, we are talking about the resistance. So by taking this example, we need to know what is resistivity or specific resistance, which is indicated by rho. So with respect to resistance, R is equal to rho L by A. That's why this resistivity is equal to R into A by L. So when the conductor is having a length of 1 centimeter, then L is equal to 1. If it is having the area of cross section that is 1 centimeter square, then it is 1. That time we can imagine that conductor like this: 1 centimeter length, 1 centimeter square area. Then that time the specific resistance is equal to resistance of the conductor. So specific resistance or resistivity is a resistance offered by a conductor which has a length of 1 centimeter and area of cross section is 1 centimeter square. Or by this we can say that resistance offered by conductor whose dimension or which has 1 centimeter cube volume, then that resistance is called as resistivity. The unit of resistivity or specific resistance is ohm into centimeter or ohm into meter. So by this we can say what is conductivity or specific conductance, which is indicated by the letter kappa. It is not K, it is kappa. So conductance we know, which is inversely proportional to resistance. So which is equal to A by rho into L, because R is directly proportional to L, R is inversely proportional to A, that's why R is equal to rho L by A. So here G is 1 by R, that's why G is equal to A by rho into L. As conductance is 1 by resistance, that's why conductivity is 1 by resistivity. That's why conductivity or specific conductance K is equal to 1 by rho, which is equal to L by RA, which is equal to 1 by R is G. That's why G L by A. So here L by A is called as cell constant. That's why conductivity is equal to conductance into cell constant. So K equal to G. So it means that this kappa is equal to G when the conductor has a length of 1 centimeter and surface area 1 centimeter square, or conductance offered by a conductor which has 1 centimeter cube volume, as we have seen in specific resistance. As we know, the unit of conductance is Siemens. That's why unit of conductivity is Siemens per centimeter. The application of specific conductance or specific resistance can be understood by analyzing this chart. So here we have taken many materials like copper, iron, silver, aluminum, and the dimension is 1 cc, 1 cm cube or 1 cc cubic centimeter, and we have measured different materials electrical resistivity or specific resistance. So with respect to copper, it is 0.034, so all are having -5, so we can ignore that one. So with respect to copper and iron is having more resistivity. Because of this, we use copper in household wirings, not the iron, because there will be dissipation of energy by the iron. We want to know the variation of specific conductance or conductivity with dilution or on adding the water. So we know as dilution increases, concentration decreases. So let's look at strong electrolytes. We know strong electrolytes undergo complete dissociation, so give ions, as we can see. So if we increase the dilution, then the freedom of ions increases, but the number of ions present in 1 cc of the dimension decreases. That's why specific conductance decreases. With respect to weak electrolytes, so this is weak electrolyte because it is undergone partial dissociation. So upon dilution, the degree of dissociation or number of ions increased, but we don't know at what part the number of ions have been increased. So we cannot determine the specific conductance of weak electrolyte upon dilution. So it is indeterminate. This completes specific conductance. So let's look at the another type of electrolytic conductance, that is molar conductance, which is indicated by the letter lambda m. So it is the conductance due to all the ions present in a solution containing 1 mole of an electrolyte at a given temperature. So here consider 1 liter water is taken. In that we have added 1 mole of substance. Now the concentration of this solution is 1 molar. Here 1 mole means if it is NaCl, then 37.7 gram of NaCl is taken and 1 liter water within which it is dissolved. Then the concentration of the solution is 1 m. So molar conductance is the conductance due to all the ions present in, like Na plus Cl minus, Na plus Cl minus. So the conductance due to all the ions present in this solution is a molar conductance. So molar conductance can be given by the formula 1000 K by M. It is not K, it is kappa. So kappa means specific conductance. M means number of moles of solute or electrolyte. So the unit of molar conductance is Siemens centimeter square per mole. We know the unit of specific conductance, that is Siemens per centimeter, and with respect to molarity it is moles per dm cube. So dm cube can be written like moles per cm cube, maybe some 1000 cm cube is equal to 1 dm cube. So that's why this is moles per. Okay, now this cm cube goes up, Siemens per centimeter into cm cube divided by moles. So here 1 goes, so that's why Siemens centimeter square per mole is the unit of molar conductance. Imagine a vessel in which 1 liter water is there. In that we have taken 1 mole of substance which is dissolved. So this is 1 m solution, and whatever the conductance we measure by using the conductivity cell, then whatever that conductometer shows the reading is the molar conductance. So we are imagining this vessel. So what will happen to the molar conductance if we keep on adding the water? So variation of molar conductance, that is lambda m upon dilution. So let's look at strong electrolytes. So strong electrolytes obey Debye-Huckel-Onsager's equation, which is given as lambda m is equal to lambda naught m minus a into root c. So here lambda m represents molar conductance, c represents concentration. So as the dilution increases, concentration decreases. So here lambda m and c are connected by this formula. So here new factor comes, that is lambda naught m. What does it mean? So lambda m, we know it is molar conductance at a given temperature or concentration. Lambda naught m represents the limiting molar conductance, or molar conductance at 0 concentration, or molar conductance at infinite dilution. It means we have taken the electrolyte, that is 1 m. We have added enough water, like it may be 1 barrel full of water. Then whatever that barrel is containing this much amount of electrolyte, which is distributed throughout that solution is called as infinitely diluted solution. So if we measure the conductance of that solution, then in that solution we have 1 mole of substance, but it is infinitely diluted. So that's why that at that time whatever the conductance is given by the conductometer is called as molar conductance at infinite dilution or 0 concentration. So A is a constant which is dependent on the solvent. So the nature of solvent may be its polarity or viscosity or temperature. So if we rearrange this formula, here we can see that lambda m and c are variables, rest all are constants. That's why lambda m is equal to minus a into root c plus lambda naught m. So this represents y is equal to mx plus c. For this represents an equation of straight line. So where y-axis represents lambda m, x-axis represents root c. So when we plot a graph, we get a straight line but negative slope. So y-intercept is called as lambda naught m. So the value here is lambda naught m. It means molar conductance of the electrolyte at 0 concentration or infinite dilution. And slope is given by my a. So this is how molar conductance varies upon dilution with respect to strong electrolyte. It is straight line. So let's look at variation of molar conductance with dilution with this example. So consider a vessel containing 1 mole of solute. So here molar conductance, that is lambda m, is given in a scale in the unit of Siemens centimeter square per mole. So 1 mole of solute, it is not containing ions, it is not a solution at all. So that's why the molar conductance is 0. When we put water, but still they are not separated into ions, so the molar conductance of this 1 mole of salt that is dissolved in the solution, that is dissolved in the solvent, is still 0. When 1 mole of salt is dissociated into 1 cation and anion, so the number of ions is still 1 mole of cation and 1 mole of anion. So that time the molar conductance increase to certain value. When we add more water, these ions got more freedom. So now these are called as diluted 1 mole of cations plus 1 mole of anions. So the molar conductance increased because of this freedom. So that's why the molar conductance increases here. But after a certain time, even if we add more water, then molar conductance is not going to vary because the ions have got enough freedom that they are out of electrostatic interaction. So now this solution or electrolyte is called as infinitely diluted. So here 1 mole of cation and 1 mole of anions are present. So this value is called as molar conductance at infinite dilution or molar conductance at 0 concentration. That's why molar conductance of an electrolyte at infinite dilution is equal to what? There are ions, that is cations and anions. So molar ionic conductance of cation at infinite dilution plus molar ionic conductance of anions at infinite dilution. So which is given by the expression lambda naught m, that is the molar conductance at infinite dilution of an electrolyte, is equal to molar ionic conductance of cation at 0 concentration or infinite dilution plus molar ionic conductance of anion at 0 concentration or infinite dilution. This is called as Kohlrausch law. So Kohlrausch law, which was given by Friedrich Kohlrausch with the mathematical expression in which the molar conductance of substance or electrolyte at infinite dilution is because of the molar conductance of individual ions at infinite dilution. It means these ions are the contributors to the total value of molar conductance of an electrolyte. So that's why it is also called as law of independent migration of ions. So these ions are acting independently to the conductance when they are diluted to infinite. So the statement says that the limiting molar conductance or molar conductance at infinite dilution or molar conductance at zero contribution of electrolyte is equal to sum of limiting molar conductance of individual ions. Here, the capital lambda naught m represents limiting molar conductance of electrolyte, whereas small lambda naught m indicates the limiting molar conductance of the ion. It may be cation or it may be anion. So we can see some examples, some cations and anions. So H plus, when it is infinitely diluted, the molar ionic conductance, it means the H plus ions, number of H plus ions is Avogadro's number, and which is infinitely diluted, it means it is not under the influence of any electrostatic force of either cation or anion or any neighboring ions. That time it gives the conductance 349.8 Siemens centimeter square per mole. Whether this H plus ion is coming from weak electrolyte, strong electrolyte, it is not going to affect the contribution of H plus ions. So similarly, the K plus is having limiting molar ionic conductance of 73.5. So with respect to anion, OH minus is also having the limiting molar conductance or limiting molar ionic conductance of 198.3 Siemens centimeter square per mole. Here lambda naught m of cation is this much, lambda naught m of anion is this much. So because of these cations and anions, there is a molar conductance of an electrolyte at zero concentration or infinite dilution. So variation of molar conductance with respect to weak electrolytes. So consider here weak electrolyte is taken and we added water. The amount of weak electrolyte taken is 1 molar. So we know when we added the water, then there will be dissociation or partial dissociation, and when we add the water or upon dilution, there will be more number of ions produced. We don't know number of ions are produced. That's why when we plot a graph of molar conductance versus concentration, it may be root C or C, then the graph is not straight line or it is not obeying the Debye-Huckel-Onsager's equation, but it is a curve. Now the question comes, where does this curve meets to this axis, which represents molar conductance at infinite dilution? It means we want to calculate the molar conductance at infinite dilution in that scale, but we cannot calculate it directly by using Kohlrausch law. So let's look at the applications of Kohlrausch law. So first application is to determine the molar conductance at infinite dilution for weak electrolytes. Second one is to determine the degree of dissociation of weak electrolyte, that is alpha. Third one is to determine the dissociation constant of weak electrolyte, that is Kd or K. So let's look at the first application, that is molar conductance at infinite dilution of weak electrolyte. because the curve didn't touch the y-axis, so we don't know when does it touch. So we want to calculate that value. But how to calculate? But by using the Kohlrausch law. We can use the example, that is acetic acid. We know acetic acid is a weak acid, so weak acid undergoes partial dissociation. So we want to calculate the molar conductance of acetic acid at infinite dilution or zero concentration. According to Kohlrausch law, how can we write it? There are two ions. Cation is H plus, anion is acetate ion, that is H3COO minus. So according to Kohlrausch law, molar conductance at infinite dilution for acetic acid is molar ionic conductance of acetate ion at infinite dilution plus molar ionic conductance of H plus ions at infinite dilution. So we can use molar electrolytic conductance at infinite dilution of hydrochloric acid, sodium chloride and sodium acetate, as these are strong electrolytes. So they will be having certain straight lines which meets the y-axis. So we can take the use of them. So molar concentration, molar conductance at infinite dilution of HCl is equal to molar ionic conductance of H plus ion at infinite dilution plus molar ionic conductance of Cl minus ion at infinite dilution. So this molar conductance at infinite dilution of NaCl is equal to molar ionic conductance of Na plus ion at infinite dilution plus molar conductance, molar ionic conductance of Cl minus ion at infinite dilution. With respect to sodium acetate, molar conductance of sodium acetate at infinite dilution is equal to molar ionic conductance of Na plus ion at infinite dilution plus molar ionic conductance of acetate ion at infinite dilution. So we have applied Kohlrausch law to all these strong electrolytes. So we can rearrange them, like it is containing H plus ion, this containing acetate ion. So if we combine both of them, we are going to get the molar conductance at infinite dilution of acetic acid. So how to do it? Let's rearrange them. So we add molar conductance of hydrochloric acid at infinite dilution plus molar conductance at infinite dilution of sodium acetate, and we subtract both of these value with the molar conductance at infinite dilution of sodium chloride. Here Na plus ion, here it is into bracket. That's why Cl minus get cancelled. So remains molar conductance of acetic acid at infinite dilution, which is weak electrolyte. So we are going to calculate molar conductance at infinite dilution of weak electrolytes by using the strong electrolytes. We are going to apply Kohlrausch law. So the next application of Kohlrausch law is to determine the degree of dissociation of weak electrolyte. The degree of dissociation is indicated by the letter alpha. So what is degree of dissociation? So it is the fraction of total molecules dissociated. Example, consider acetic acid which is undergoing dissociation to form H plus and CH3COO minus. Here consider there is 1 mole of acetic acid. So out of 1 mole, 0.1 mole is dissociated into H plus and CH3COO minus ions. So alpha represents 0.1 divided by 1, that is equal to 0.1. So this is degree of dissociation. Or we can say that 10% is the degree of dissociation of weak electrolyte. So as the dilution increases with respect to weak electrolyte, the degree of dissociation increases. It means the fraction of total number of molecules dissociated becomes more. It may be 0.1, 0.2, 0.3, 0.4, 0.5. It means 50%, 10%, 20%, 30%, 40%, 50% of the total number of molecules have been dissociated. The question comes how to calculate it by using the molar conductance. So there is a formula, that is alpha is equal to lambda m divided by lambda naught m. So lambda m is the molar conductance at given concentration, lambda naught m is the molar conductance at infinite dilution or zero concentration or limiting molar conductance. Here lambda naught m for weak electrolyte is already calculated by using first application of Kohlrausch law, and lambda m can be calculated by using the conductometer experiment. Then we can understand the alpha or fraction of total molecules dissociated. Next application of Kohlrausch law is to determine the degree of dissociation of weak electrolyte, that is Kd. So it is calculated by using the formula Kd is equal to C into alpha square divided by 1 minus alpha. So where C is the initial concentration of a weak electrolyte and alpha is the degree of dissociation. So we already know that alpha is calculated in second application of Kohlrausch law, that is lambda m divided by lambda naught m, but lambda m is calculated in the first application of Kohlrausch law. So all are connected, 1, 2 and 3. So if we calculate the lambda naught m, we can calculate the alpha. By that we can calculate the Kd. Within that we are looking at the conductance. Within that we are looking at the electrolytic conductance. Within that we are looking at the types. In that this is molar conductance. For strong electrolyte it applies Debye-Huckel-Onsager's equation, but for weak electrolytes we are applying Kohlrausch's law. So we are here. With respect to weak electrolyte, the dissociation can be written as H plus CH3COO minus, we have taken acetic acid. So alpha represents lambda m divided by lambda naught m. Here lambda naught m is given by Kohlrausch's law. So what about lambda m? So lambda m is calculated by using a cell called as conductivity cell. Okay, so this is the conductivity cell and this is conductivity meter. This shows the specific conductance, that is K, of this solution, whatever the solution at given concentration. So K is calculated here. It is having certain value, Siemens per centimeter. So we can calculate the lambda m by using the formula 1000 K by the given concentration, whatever the concentration of the solution that is taken. So m. So by this we can calculate the lambda m, that we can put here, we can get the alpha. So if we take this alpha and put it in this, then we get the Kd. So this completes molar conductance. That completes the molar conductance. So let's look at the last part of our electrolytic conductance, that is equivalent conductance, which is denoted by the letter lambda E So lambda E is equivalent conductance. So the definition of electrolytic conductance is, at a given temperature, the conductance due to all the ions present in a solution containing one equivalent weight of an electrolyte. So lambda E can be given by the equation 1000 K by E. This is kappa. So what is kappa? It is conductivity or specific conductance. E is the number of equivalent weights of a substance taken